if more students join. Otherwise, we'll just start. Okay, so let's start with the session. If at any point my voice is not clear, please let me know immediately so that I can either switch the network or sort out whatever issue it is on my end. And
Can you just update the seats of recording? Google Sheet.
can you please repeat?
Can you please update Google Sheet recordings of CT session?
Okay, I will have to ask the recording team to do that. So, okay, I'll pass on the message. But apart from that, every session that is there, right, you can go to the calendar and then check out the YouTube link there also.
I am talking about TA session.
Okay, so TA sessions, I think you will have to talk to the TA themselves then. Maybe in a TA session, you can ask them to update that sheet. Okay, so
I'm sorry for the disturbance, but your voice is too low, I think so.
is that true for everybody or is it just for some students?
No, ma'am, it's
It's
clear.
fine.
Okay, so maybe you can check, whoever is having the issue, maybe you can check it on your end once. Is my screen visible to everybody? And I would like participation from everybody because since the revision session, it is expected that at least once, I think you have gone through the contents of week 1 to 8, or if not, maybe the last few weeks, it is expected that since you've given quiz 1, at least the week 1 to 4 concepts should be very clear to you. So I'll brush through those concepts a little quicker as compared to the other ones. And from some previous sessions that I have taken, I do have some notes also. I try to reuse them so that I don't have to write everything from scratch, and that will take up a lot of time. But at the same time, I will try to cover up whatever is not written. Okay. So just give me a second. I want the session to be participative. So there are two things. Why? First is that I should get an understanding where you guys are getting stuck if you have any doubts. So if I just keep speaking and you just keep saying yes, no, it doesn't give me an idea of whether you're actually getting the understanding or not. So if I'm asking questions, I want answers to those questions. It isn't rhetorical that okay, I'm asking something and you expect me to answer it. So I would like some participation on that. And second thing is that when I'm sharing my screen, I am on a separate tab and I'm not able to come back again and again to see what is happening here. So if I don't get a response for a long time, I might assume that there's some network connection so that you're not answering. So to avoid those, let's keep it participative so that I know that some input is coming from your end also. That being said, I also expect that you will be civil and not everybody will start speaking all together, unmuting yourself. So try to be, I mean, I'll leave it up to you. I'm not enforcing raising your hand and I'll call on you and then you can answer kind of a system for now, just not to hinder the flow. But my expectation from you is that you will be civil and you will not speak over others in that scenario. Okay, so starting with the session. So
Excuse
there
me,
are,
ma'am.
yeah.
And today's agenda session is to division of week 1 to 8.
Yes, so I'll be doing a revision for quiz 2. Quiz 2 syllabus is week 1 to 8, but at the same time, more emphasis will be laid on the part that has not been covered in revisions till now, which is week 5 to 8. For a comprehensive revision of week 1 to 4 from scratch, you can refer to the quiz 1 revision recording also. But I will still be touching up those topics. I'll still be revising those. So if you have doubts, please do ask. But I'll try to give more time to week 5 to 8 because that is new currently for this particular quiz, and the weightage for that will also be a little bit more.
Okay, ma'am.
And more than anything, we'll try to keep it conceptual. Yes, the quiz is important, but what is more important is this is the basis of a lot of the courses that you'll be taking up in the future, namely Python, PDSA. So the main point is not that, okay, what do I write in the quiz or whether this will be correct in the quiz or not. That is also important because, again, that is an evaluation method that we are using. But what is more important is whether you are understanding the concept or not. So rather than focusing on the nitty gritties, we'll try to see why we require computational thinking, the overview picture of week 1 to 8, what we are trying to solve, why do we need dictionaries, why do we need lists, why were variables not enough, and again, the limitations of the different kind of methods that we are dealing with. We'll try to see a bigger picture of things rather than focusing on uh, basic syntactical things. Those are important, but for those you can refer to the slides. But what we want to understand here is the need. Okay, so based on that, I might not go in a sequential manner from week 1 to 8, like, okay, this is what week 1, this is what week 2 covers. So those, again, you can refer to the slides. That's pretty obvious. We'll try to work based on the needs again. So the first thing which is very important is I'll refer to the already written things as and when needed. So for now, let me start a little bit from scratch itself, trying to, okay. So data, that is one very important thing. So you are doing a course in data science, right? So one of the most important things which we will do the computational on when we talk about computational thinking, We want to think in a certain way that we are doing our computations, but what are we doing our computations on? Data. So data is an important aspect. From week 1 itself, you must have been introduced to many data sets, right? And what are we doing with data? We are trying to do some computation on that data in the form of, so some flow is there in which we will try to go through the data. We can either do iteration, we can do filtering, we can aggregate the data together. We are writing pseudocodes in order to represent that algorithm or the way in which we are handling the data. We will see data in the form of tables. Then we will see procedures, nested iterations, binning, lists is there. List is basically something in a data structure, right? So we are giving some structure to the data that we have. And then we have sorting of that particular data. Then we have dictionaries and we have side effects. So this is the overall agenda of week 1 to 8 that we have done till now. So the first thing is the bigger picture, right? So why, again, if we talk about a basic algorithm, so imagine that you have a table containing information of around, let's say, 10,000 students. And there are some questions about those students that we want to answer. And in order to do that in a logical, in a sequential manner, we need to have some computations to be done on that data that we will do in the form of a pseudocode, right? So the basis of what we're trying to do is that we need some structure, pseudocode, or a flowchart to determine what we are going to do with that data, what computation we have to do. Okay. But before doing anything, before writing any algorithm, before writing any pseudocode, what do we want? We want to understand the data, correct?
Yes.
Okay. So in order to understand the data, we first see that there are multiple data types, right? So taking an example of the student data that we have, I'll try to copy paste something which I already have. Let's see, do that properly here. Yeah, so this is visible, right? So this is, let's say, one particular student data that we have. We've already seen such cards, right? Different data sets were there. One of the data set was a sequence number was assigned to a student. The name of the student was there, the gender was there, some date of birth was there, which, say, like this, let's say 01012003. Okay, let's say something I have scored in maths, I've scored in physics, chemistry, and the total score. Now, in order to understand this data, what is the first thing that we can ask about this data? Look at all the fields that are there. So first of all, I hope all of you are clear with what a field is and this is basically a card, right, which is given to us. So in that card, let me go to the revision one that we had. Okay, so this was one example that we had taken at that particular time, right? So everybody knows what a row and a column is. That much I think it is expected that you should know till now what a row is and what a column is. Correct?
Yes, ma'am. We already know it.
So basically, one particular card which I was representing there, a student card, in a table that would represent one row, but all the attributes or all the fields that are defined in that card, the maths, physics, chemistry, the student name, the date of birth, gender, all those are attributes. So now, when I go back to this particular data that I was talking about, just give me a second. Yeah. So now when I talk about this data, then these are all the attributes. The sequence number, the name, the gender, and all these things are the attributes. So all these attributes have some data type, right? So this is
Yes,
what
ma'am.
week 1 covers, the certain data types that are there. So now, of course, every field cannot be an integer. Some you see are integers, some are strings. For example, Ravi is a string, gender is again a string, but it can take only 2 values, male or female, so M or F. DOB is again another data type, and again maths, physics, chemistry, total are integer data types. So again, different data types are there. We have Boolean, we have integer, we have character, we have string. And a data type is not just about how the computer is storing that value, that okay, will this come under string, will this come under integer. What is important to understand in a data type is it tells us what operations make sense on that particular data. So when we talk about sequence number, right, even though this is an integer, if we go more in depth in the subtypes or sanity of that particular data, we will try to understand that just data type validity is not equal to semantic validity. For example, let's take this example for maths. We have 87 marks in maths. Now 87 is an integer, correct?
Yes, ma'am.
So 87 is an integer data type, that is true. But at the same time, let's say I say maths is equal to 250. Would that make sense? It is an integer, yes. Is it following the data type validity? Yes, it is following the data type validity. But can maths marks be something like 250?
No.
No. Why? Because the cap is 100, right? So semantic validity is that given the context of what maths is, the data is not sane. Even though it is valid, we can put that value there, but it is not sane. Right? Similarly for DOB, let's say I try to input 30th February, 31st February. That is not a sane data, correct? Maybe that type will be satisfied that, okay, we have numbers separated by strings or something like that. Maybe that particular condition of how a date should be, it is satisfied. But at the same time, the data is not sane. You understand that part? What sanity of data is? Guys,
Yes,
some
ma'am.
participation, please.
Yes, ma'am.
Yeah. So the data has to be seen also, as well as it should be semantically correct. Now, the next thing is that the kind of operations that make sense on that data. So again, on integer, we have addition. We can check whether something is greater than, whether something is less than, so stuff like that. On things like name, gender, DOB, we check more of an equality, that okay, is this given string equal to M? If so, we know that it's a male gender. On sequence number, even though it's an integer, operations like addition, subtraction, they don't really make sense, right? Here we talk about filtering, accumulation, and stuff like that. So we have to notice, again, we can add integer to integer. We can't add name and maths marks, right? That doesn't make sense. So knowing the data type of different variables or of different fields tells us what operations we can do on those fields, whether in a combination to others or by themselves. Okay. Now again, when we talk about data types, there comes a notion of subtypes. So like we said, right, maths is marks. So by default, it's an integer. So the data type is integer. But when I talk about maths, we have some restrictions on that data type itself. It should be greater than 0. It cannot be negative. If we assume there's no negative marking, then that cannot be negative. It has to be less than 100, let's say. So there are certain restrictions on that mark. So 250 is an integer, but it is not a marks subtype of a data type. So a subtype basically gives additional restrictions to a basic data type. For example, DOB, if let's say by default it's stored in a string format, let's assume, for the sake of this example, then when we talk about the specific DOB data type, then it has some restrictions on what that format of that string will be, what values it can contain, and stuff like that, right? So, okay,
Yes,
now the next thing is the notion of a record. That is the same thing that I had discussed earlier also, that a student card is having multiple fields. So instead of storing it in terms of many variables, right, that okay, student one sequence number, student one name, student one gender, we try to club them, we bundle them, and that is what a record is, right? In a table, a record is one particular row that we talk about. So having multiple such records give us a structured way of keeping that data. So again, these are motivations for data structures like list, for example, that okay, one variable is not enough, or storing multiple variables for one particular student is not enough. So rather than that, we can have one list per student. Okay, whether it makes sense or not for computation is a separate question. We'll discuss that later. But one list is basically that we want to keep a certain record that says that okay, all these things inside that list are connected in some way or the other. So rather than, if suppose a student, in this case, let's say, how many things are there? 1, 2, 3, 4, 5, 6, 7, 8. So 8 fields are there in a student card. Rather than having 8 different variables for that particular student, let's say student 1, we can have student 1 as a list itself, and then we can have all the details of that student in a sequential manner. That is one way. Another way could be that instead of having the student as a list, as the list name, we can have the name as a list name and then store all the student names as the list. We'll see the limitations, we'll see the benefits of this later. This is just a way of introducing lists. Okay. Now, the next thing is that we are trying to process all the students. Instead of list, now think of things in a table format. So coming down to a particular table format. So this was one example that we had taken earlier also. Campus bites, again, we had serial number, we had dish names, we had price of the dish, we had whether that dish is vegetarian or not, and the spice level. And we had defined the data types. So one is integer, one is string, one is integer, boolean, and character. And then again, there will be some subtypes inside that also. Okay. So we know what row are, we know what column are in this, and this is a menu table. So the structure of the table, everybody understands till now?
Yes, ma'am.
Okay. Now, let's say that I want to do some computation on this. I want to find out, let's say, something like what is the maximum price? What dish has the maximum price? Or how many dishes have spice level of spicy? So these are some random questions that we have data, we have questions to ask, we can get answers from that data, correct? In order to find that answer, we write something called a pseudocode. But before a pseudocode, we also see a notion of a flowchart, correct? So flowchart is something that we started with, correct?
Yes, ma'am.
Yes.
So let's say this is what I'm talking about. So this one doesn't have a spice level. So again, a food delivery setup example is there. And we have an order ID, we have restaurant, we have category, we have bill amount. I am assuming that you have understanding of this X dot order ID notation. For one particular card, X, the field order ID is there. So X dot order ID, and X will keep on repeating as we shuffle the cards, or as we go through the cards. So pile 1 is unseen cards. So this was one example. And then from this particular pile, things keep on moving to the active or seen pile. And we do some kind of computation. So a basic problem statement was that we want to find out the maximum bill amount. Okay, so this is the structure of a flowchart. So we start with a node which is called a terminal node. So the start and end, both of these you see they are in a different shape. Rounded bracket rectangle is there. So this is called a terminal node. Apart from this, we have the process. Process is something that is changing whatever is, so some variable name it is changing, right? So max amount is initialization is happening. Let's say I'm talking about pick a card X from pile 1. So some structure is changing. Here we are the 7th step, right? Max amount is equal to X dot bill amount. So something is changing. So this is a process that is happening, right? So this is a square bracket, a square notation that we're using. Then we have decisions. So what path to follow? So some decision has to be made. Are there more cards? If yes, we'll do something else. If no, we'll do something else. Is the bill amount greater than the maximum amount? If yes, then we'll move to some particular block. If no, we'll move to some other particular block. So some decision has to be made about what path execution we want to follow. Arrow is the execution orders, and again we come back to the terminal, that is end. So the flow for this was we start, we initialize, we check whether there are more cards in pile 1. If no, then again it ends, right? Nothing to do there. If there are more cards, then we pick a card X from pile 1, and then we check whether that particular card is great, the value of bill amount is greater than the current max amount. In this case, it will be, because max amount is 0 currently. If yes, then we make some updates. So we want to find out the order ID, right? So we will first keep the count for max amount, at what is the current max amount which is there, in order to compare for future iterations. And we want to update the order ID so that we know which order has the maximum amount. So this flow should be clear to you. And similarly, this flow is something that I have tried to write in a step-by-step format. That to find out the order ID with the maximum bill amount, these are the steps that need to be followed. So this is just writing in a normal format. Now pseudocodes, why do we need pseudocodes if flowcharts are there?
For making large data sets. We are making only
Exactly.
small processes.
Exactly. So flowchart is good enough till the time that we have limited number of steps, or the computation is simple enough, or the data is not that large. But when we have something very large, when we are doing multiple iterations, when we have multiple fields, this particular flowchart can get very big. Okay, there might be some repetitions that we want to do. There might be some code that is repeating and stuff like that. So pseudocode is a way to introduce simplicity to big amounts of data. So what we are doing in this much space in a flowchart, right? This is all it takes to write that in a pseudocode. To get maximum amount in order ID, this is simply the pseudocode that which we are following. But again, when we talk about pseudocode, even though as compared to programming languages, there are a lot less restrictions on a pseudocode. We can write things like, while pile 1 has more cards, right? Pile 1 has more cards. So there, I rarely feel that there might be a programming language in which you can write something like this: pick a card X from pile 1. This is not how they work, right? There is some structure, or there are some certain rules that, okay, this is how you have to write. So in that way, a pseudocode is very forgiving. You can write things like, okay, pick a card X from pile 1, or move to pile 2, reorder, shuffle. Things like this can be said, basic English language that we understand. But at the same time, there has to be some order. There has to be some structure. That is where pseudocode is similar to a code, but again, not as rigid as a code. So some block of logic is, let's say if something is getting repeated, or if something is inside a block, that okay, if this fulfills, then certain lines have to be executed. So those lines have to be clubbed in some manner, right? So we use things like curly braces. We use keywords like while, if, which means something consistent throughout the pseudocode language. That even though we're not using any language, it's language agnostic. But within the pseudocode rules that we are defining, keywords like while, if, for, right? These things mean something. How we assign things, how we check for things, all these are certain rules. So we, even though we are saying start and end, that is there, but initializing a variable max amount is equal to 0, there is a certain way to initialize. We can't say 0 is equal to max amount, right? We write the variable name, we say equal to, we assign the value. Then we have while. So the condition for while will come under these brackets which are there, round brackets which are there. And whatever has to be executed while this condition is true, all that comes under a curly braces. Within this, let's say I'm picking a card, there is some condition also. So then that condition gets checked. Then within, if this condition is fulfilled, then we are executing some other lines. So the 7 and 8 line will get executed. They are inside a separate curly braces bracket. So understanding the structure is very important in order to understand the pseudocode. So when do we use while? When a block of logic is meant to repeat till while or if statement is true. Okay, so when we say about till, then we say while, or when we talk about one certain condition, that okay, if this is getting fulfilled or not, only once we have to run it. In that case, we use if. Okay, now variables is equal to value means that the value is being assigned to that variable. When we are checking the value, then we do double equal to. That is different. Okay. Again, this is called a filtering condition. This thing that we used here, right? X dot bill amount is greater than equal to max amount. If it is true, this will return a Boolean expression. If this is true, we will enter the if loop. If it is not true, then directly from 6th line, we will move to the 10th line and we will skip whatever is inside the execution of the curly braces of if. This filtering condition needs to be fulfilled first. This is a basic pseudocode. Okay. So again, equal to is for assignment, double equal to is for checking whether it's true or false, something we discussed. Then we can keep some variables, we can update those variables. Again, iterations we talked about. So now when we talk about iterations, right, what are iterations? I'll try to come back to the revision slides that we had. Here. So we had some week 1 to 4 revision. So in week 1 to 4 revision, one of the core things was we talked about what an iteration is, what filtering and accumulation does, and what a function or a procedure is. So firstly, in the pseudocode itself, we saw iteration. So an iteration basically means that we sequentially go through the records to keep track of some variable. Okay, so we initialize, we repeat the steps for each record. So certain steps are there which we are repeating for each record, and then we have some termination condition for that iteration. Filtering is we basically add decision to our loops. That okay, if this is fulfilled, then we'll do this. If this is not fulfilled for that record, we might just skip that record. We don't want to do anything for that. Accumulation aggregates some value. Sum is there, average is there. All those things are done by accumulation. So something which we are doing for all of the records that pass some condition. So we might say that we want the sum of all the boys. So there is some filtering condition that the gender should be M. And when that filtering condition gets fulfilled, we are accumulating the marks, let's say, for that particular student to a variable sum. So both of these things can happen simultaneously. And function and procedures are when we want to avoid writing repetitive code that has some minor differences. So let's say some parameter is changing, but we want some reusability of that code. Same logic is getting repeated for multiple fields or records, let's say. Then in that case, we write a function or a procedure. It takes something such as in this case, it was target spicy status, let's say, and it returns something. It might not return something. It might not take a parameter. Both are okay. It might take multiple parameters. It might return multiple parameters. That is also valid. Okay. So this is how you write a function a procedure. This is how you call a procedure. So these are some basic syntax that you can notice here. Going through this, consider two files with identical data, file 1 and file 2. This is the condition. Here I want to know what is iteration, what is filtering and accumulation, and then we will move on to the procedure part also once. So this is again time for participation. I have spoken for around 30 minutes now. Now it is time for you to let me know whether this is clear or not. Once this is done, we'll move to week 5.
The start and end box both are considered as terminal.
Sorry, can you repeat?
The start and end box, the both are considered as a terminal. Isn't it?
Yeah, both are considered as a terminal. Let's skip the start part. So first we are doing some initialization. That is okay. Then we initialize a list also here in this case. Okay, and now we want to do some. So what is while here? I just now.
While here is you will iterate through every card till you are you finish with the cards.
Yes. So while is an iteration, right? Now inside while, we see one more while. What is that?
Double iteration for comparison.
Yeah. So we have something of a nested nature here.
Yes.
So in order to
Yes.
compare two things, we are having two while conditions here. Okay. And in that also, we were saying that two piles were there of identical data. So let's say I printed one full set of my stack of cards which were there, and then I printed the same stack again, and now I'm using both of them in order to compare prices. Right? So there was some logic that I'm doing. Can somebody explain me what that if logic is here? The first if logic. What have I written inside this? What does it represent? What is happening here?
If the price is equal and the serial number is not equal, we will enter into the if block.
Okay. And do you understand the logic behind this? Why we are doing
Different
this?
item with equal price.
Yeah, so we wanted to figure out which two dishes are equal price, but at the same time, the logic that we have written, we saw that the same card can be compared with itself also, right? In the very first iteration, let's say the order is same, right? Identical data. So we pick something from pile one, then we pick the same card from pile two also, right?
Yes,
Correct?
ma'am.
Then they are identical. So of course the prices will also be the same, but we don't want to consider that because they are not different dishes. So we check the serial number should be different. Then what are we doing in the next line? Let's say if condition gets fulfilled. So we will enter that block.
Yes.
So what are we doing in that block? How big is that block? How many lines have come in the if block?
3 lines. We are
Okay, 3 lines are there.
assigning.
What are we doing in those 3 lines?
We are assigning dish 1 and dish 2 and keeping them in the equal price pair.
Okay, so what exactly is dish one here? What is x1 dot dish name? Which of these is a variable? Which of these is a constant? Or are both of them variables? Are both of them constants?
Dish name are variables, and dish 1 and 2 are also variable, I think.
So does everybody agree with that? Anybody who would
The
like
this
to?
one and this two are variable, and the this name and this names are constant.
Sorry, dish name and dish name are?
And this name are constant, and this one and this two are variable.
Okay. So dish one and dish two, if you see carefully in the beginning, whatever we are initializing are variables, right? Something that we can change throughout. So dish one and dish two are definitely variables, but then we are assigning those variables some value. Now, where is that value coming from? For the people who are saying that that value is a variable, it is not, right? The data is fixed. We are not changing the data. We are just doing something from that data, correct? We are assigning it to some variables. We want to do some computation on that data, but we are not changing the data itself, correct? We are not reassigning marks to that person. Sorry, your voice was not clearly audible. If you're speaking something, can you please speak a little louder? Was somebody saying something, or should I continue?
So suppose the x1 dish name is paneer and x2 dish name is suppose a fried rice. Then both are not the same thing. They are variable. They will vary.
Yeah, so they're supposed to vary, right?
Yes, so they are variable only, na? X dish name.
No. Variable here means something whose value we can override. So whatever data we have been provided, that is fixed. So when I'm talking about x1 dot dish name, so whatever card x1 I am referring to at that particular point, I cannot change the content of that card. That card is fixed. For card x1, if dish name is paneer, I cannot change the dish name for x1 to fried rice in that case. I can only change what I assign to the variable that I initialized. which is dish1.
Okay.
So dish1 is variable, but x1 dot dish name is that I'm reading that particular card, and whatever data is there inside that card, I cannot change. So I can just assign that value, but for the intent and purpose of this pseudocode, the value of x1 dot dish name will be a constant. I cannot change that value. I'm just reading it from somewhere. Okay.
Okay.
Again, if we let's say that it can be variable, then that's a different thing, that we want to change the data. But in this case, we don't want to, right? We are reading from cards. Those cards are fixed. In the lectures also, you might have noticed, right? The professors are handling different cards with each other, right? But do you see them cutting a certain value in the card and changing it, that okay, these marks, maths marks, I want to upgrade, this is 58? That is not happening, right? We are keeping some lists, we are making some averages, we are keeping some conditions. Based on that, we are changing the variables that we are assigning. Whatever they try to write on the different cards, but the printed cards, they remain the constant, right? So that is our source of truth. We don't want to change that. Now, let's say we find dish1 and dish2, and then we are adding this pair to equal prices. Now, currently, I have written this in the form of a pseudocode, because till that point when I discussed this example, we had not covered lists. But now we will see that this can be written in a separate syntax also. So basically, it could be equal price plus plus whatever that dish1 dish2 pair is, that can be added to the list. Correct?
Yes, ma'am.
Okay. So then we come out of that particular if loop, and now we are inside the second while loop, the inner while loop. And in that, we move x2 to pile 4. So some pile 4 is there, which again is seen data or something. Then reset pile 2 with pile 4. Why are we doing this? We are not resetting pile 3, but we are resetting pile 4. Why? Sorry, pile 2. We moved x1 to pile 3. Pile 3, we are forgetting about it. We are not doing anything with pile 3 in the whole setup. It's just a random pile where we are putting stuff and not looking at it again. But when we talk about pile 4, we are resetting pile 2 again with pile 4. Why are we doing that?
Have to compare it with the next
Yeah, so
card
we have
in
to
pile.
compare it with the entire data set, right? We want all the possible pairs. So for the second one, I want again, for whatever second dish that I have, the second card of x1 pile, the first pile which we had, right? Pile 1. So we want to compare it with everything in pile 2. So now in the case of the second while list, pile 2 was changing, right? So whatever pile 2 was changing, I did not want to compare the new x1 pile with the updated pile. So I have to reset it to have all the cards. This is why we have to reset it. So I hope this part is clear to everybody. Now coming to procedures. So any doubt till now, first of all? Any doubt? No is also an acceptable answer, guys.
No, ma'am.
No.
Okay. Now coming to functional procedures. This is a basic procedure, find max price by preference. So this is the syntax of writing a procedure. We define the name procedure, then we write the name of the procedure. Then in the bracket, we have the parameters that can be passed to that particular procedure. Okay. So just give me a second. So here, if you notice that we are doing the same computation, but on different values of that field. So spice level is there. Spice level can have value M, S, L, but based on all those values, I want to do the same computation. The logic is the same, but I want to do that same computation on different values of target spicy status. So we don't have to rewrite it again and again. We can just write it all together and then we can call it based on the operation that we want to do. So we wanted to find out the problem statement here was that we wanted to find out maximum price, but based on the category preference, if preference is spicy, if preference is let's say medium, or if preference is low, spice preference is low. So in all of them, the logic of finding the maximum is same. Only what is changing is this, right? Target, if x dot spice level equal to target spicy status. So in this, target spicy status is a parameter that we are passing. And then that parameter is used as a variable inside the procedure. And if that passes, then for that particular filter, we are doing some other computation, and we are returning something which will be assigned to this variable here. So here we are returning dish name. So spicy max name is equal to, this is the calling of that function, and whatever will be returned through that function, then that spicy max name will have. So let's assume that this particular whole thing, find max by preference. Let's say when the preference is spicy, in that case the maximum price is what? Mutton biryani. So at the end, spicy max name will hold the value mutton biryani. Okay? Understood?
Yes,
Repeat
ma'am.
this.
Did somebody say something?
React it, please.
Sorry?
Repeat it, please.
Okay. So what part did you not understand in function procedures? Can you specify so that I can explain in maybe a better way?
Due to internet connectivity, I wasn't like, my connection is
Okay.
on and off.
Okay. So basically, I explained that this is a procedure. A procedure can also be called a function, and the purpose is to avoid writing repetitive code. So if the same logic I am implementing for, let's say, different values of target spicy status, but only variable is target spicy status. So we will pass this as a parameter itself, and then the same logic will repeat for different spicy status, and this is the way of calling it. This is the way of calling that particular procedure, the green part, and if the definition is given above. So whatever is returned here in dish name, so this is how we will call it. We will pass the parameter s, and then whatever is expected to be returned. In this case, what is expected was mutton biryani. So spicy
So
max
the
name.
if x dot spice level will give the spice level of the entity.
Yeah, x dot spice level will give me the spice level of that particular row which I'm talking about.
Yes.
So per row,
that is-
and if that is
per
equal to the one which we want, then we will move forward in that computation. Otherwise, we will move to the next row and then check whether it's there or not. So this filtering I'm doing here, right? So filtering is based on the parameter that I'm passing, but that parameter is not fixed. That is a variable. But for one particular function call, it will be fixed. But I don't want to write this code again and again, right? In my overall code, I want to do this for multiple spice levels that are there. I want this code to be functional for multiple spice levels. So in this case, it is variable or a parameter, we call it. But once that parameter is entered, then for the sake of this particular code, this value of target spicy status is fixed.
And where we are considering price condition?
Here, right? If x
Yes.
dot price is greater than max price, so we want to find out the maximum price for that condition. That for all the spicy dishes, which is the most expensive.
Okay.
Yeah. So this is what a procedure is. So I hope at least this much is clear. So this covers basically most of week 1 to 4. Coming to week 5, the intention of week 5 is why we need lists, right? So till now, in week 1 to 4, what we were doing was, we were working with variables. We were storing max, we were storing some average, we were doing let's say maximum, second maximum, third maximum, these kind of things we were doing till week 1 to 4. But now when we come to week 5, something called a list is introduced. Correct?
Yes.
Yeah.
Also till week 1 to 4 there was another topic for side effects, so that will come again in week 8 also actually, so that is why I skipped it for now. But more or less it's basically that whenever we are trying to do some computation, we have written some pseudocode, right? If by any chance we change something which we don't intend to change, for example we are working with a list, and or we are working with some, let's say some certain variable we are working with, and in that pile we do some changes. For example, we saw, right, where we are moving pile 4 back to pile 2. So let's say that I change the order somehow. When we say move, we are not defining an order, right? Let's say we change the order somehow, whether it was earlier in increasing order of sequence numbers, now it is in decreasing order, or it's a shuffled order. We are making some change due to our computation. There has been some change in the data which was not intended. So that is called a side effect, that something changed outside what we wanted to do. And sometimes it could be intended also, but most of the time when we talk about the word side effect, it's something which we didn't want. If it is intended, then it is the functionality itself. Okay, but just remember the side effect word. It will come back when we talk about lists and dictionaries. That is where it makes more sense. Here it is just that, let's say the procedure, whatever we are using, it is changing some table or list or pile which we are doing. More or less, it will be the order that will be changing, or we will be removing some records from the particular thing. The data might not be changing as much. Okay. So now the intention for lists we were talking about. So let's say this is some data which we have, some college data, that okay, there is some ID, there is some name, branch, year, city, coding, quiz, gaming. So the problem was that there was some fest that was happening, and in that particular fest there were 3 parameters based on which, so 3 competitions in which students can participate. So let's say a particular student participated in coding, quiz, and gaming, and based on all 3, let's say we are trying to find out a student who did well in all 3, who did well in let's say coding and quiz, but not so much in gaming or something like that. Right. So this particular data was there, and problem statement was that we wanted to find out max marks in each category of competition. So in that case, variables are there, right? 3 variables are there. So in each category, for each category, there will be 1 variable for max marks. Right? Coding max is there, quiz max is there, and gaming max is there. It makes sense. Why? Because we know that there are 3 variables only, maximum. If there are 3 parameters, there are 3 fields that is fixed, correct?
Yes, ma'am.
But let's say we want to know how many students were present from each city. In that case, in the current data that we are seeing, we know that okay, we have Delhi, Chennai, Mumbai, Delhi, Pune. We see that there are okay 4 variables that might be possible: Delhi, Pune, Mumbai, and Chennai. But for a bigger data set, for unseen data, or when we don't know what all possible value city can take, there can be many cities, right? Maybe in these 5 examples, we are not able to see all the cities, but there could be many more cities. In that case, having 1 variable per city is not suitable.
Yes.
Right? So what could be a better way?
Storing them in the form of list.
So when we say list, right? So we had Delhi students coding. So in that we had all the Delhi students across coding. We can see that this example is there. This is separate to how many students were present from each city. So this is different, of course. When we talk about how many students, right? So again, we have to keep some count based on the city. So this problem needs to be defined in a better way. Are we going to record the IDs of the students, or we just want to know how many students were there? If we just want to know how many students were there, in that case, what we can do is we can first have a list of all the cities, or rather now that you know dictionaries, right? So you will notice that this particular problem is better expressed in a dictionary, don't you think?
Yes,
So
it can be.
now with the current information that you have, initially we did not know about lists, we did not know about dictionaries, we only knew about variables. So the first instinct comes that okay, we will have 4 variables, 1 variable for each city, and that variable will hold the number of students, we will keep incrementing that, but that does not make sense. So what does make sense? Can you think of how this would be represented as a list? So if you notice, even though I've introduced this problem, you might have seen that I haven't really written a list for that. Why? Because it's not a list problem, right? It's more of a dictionary problem, where we store each city as a key, and then that key value gets updated with each student. Because we don't know how many cities are there beforehand. We will need to keep updating the dictionary, but then again, for this purpose of this problem, one particular city is a key, correct? It's unique.
Yes.
Right? But now then again, the purpose is lists first. Why do we need lists? So list is basically when we want to store multiple values of the that are needed for computation of that category. So for example, where we are talking about students from Delhi, we want to store all the names, or let's say all the this particular ID of all the students from Delhi that are doing coding.
No.
Can you please mute yourself if you're not speaking? Yeah. So then, yeah. So first we wanted to do some, let's say we want to do some computation that the particular competition that we are looking at is coding, but we want Delhi students only. That whoever students came from Delhi, let's say the teams are in such a way that okay, some college from Delhi has entered students, some college from Chennai has entered their students. So whoever has come from Delhi, all those students, how did they perform in coding? So for that, I need some parameter of all the students. We don't really want which student was which, right? We don't want to know that, okay, how much did 101 store, how much did 102 store? No, I just want to know overall what the values were, what the marks were. So in order to do that, we can just keep storing all that data in a list, and then we can think that, okay, what are the computations that we can do on this particular list? Now we can find the sum, we can find the maximum, we can find the minimum, we can find the average. Now, what is the benefit of making that list instead of directly finding this? Anybody?
If you have more than one value, you can't compute.
Sorry? Can you please repeat? Somebody was trying to say.
As it's written, to find the sum, max, minimum, average of the marks of student from Delhi or any city.
Yeah, that I understand, but why is making a list better? We were initially, before introducing the notion of lists, we were
It
already
could
finding
help
some max,
you
minimum,
to
average, right?
get a visibility on at just an instant. So that way it's easier.
To organize the data, ma'am.
Also,
Okay.
it would don't have to repeat the loop time again and again, because
Yes,
if
that is the
it's
answer I'm looking for. That even though for doing the computation, we will have to still apply the loop on the list. So for each keyword, we will use to iterate through the list, and then we'll still be finding out the sum, maximum, minimum, average. But then this list itself is a filtered version of the data. So if we want to do this again and again on the whole
Also-
data, in that case,
if you sort the list, then you would be having either in the ascending order or descending order.
yes,
So just at a
exactly.
glance, you would be able to tell like what is the highest mark, what is the lowest.
Yes. So on lists, we have certain other computations also, right? We saw init was there. We saw that we had first, we had last, such computations which we can do directly on the list, and then we can do sorting also on the list. So such things were there, correct? So whenever we have data in a structured format, so list is a data structure. By that we are giving data some structure that will help us do some computations on that data. So one benefit is that we are already creating a filtered view of what we want to do, and we are storing it as a variable, which we can update. We can add more values to it. We can remove values from it. We can do some computation on those values, right? And the other thing is that basically we can do some iterations on this data itself and try doing some max minimum average. Okay. Now some syntaxes were here. So again, key part of revision for week 5 is knowing how to initialize a list, what is an empty list, whether list can have numbers, if list can have strings, how to use a list in a pseudocode. So for each keyword is important. So for each X in dummy list basically means that if this is a dummy list given to me, then for each X, so X will be first 2 in the first iteration, then 6, then 1, then 9, then 0. And then we are appending that to the sum continuously. So dummy list is equal to dummy list plus 3. So what is plus here?
Adding that element into the list.
So how is it different from plus?
Append map. It's like
Plus
it's adding.
means you are appending, and this you are incrementing. Like,
so plus basically is not something which can be used for lists. Plus is something which we use for variables, right? So integer type variables specifically. So if we say here, right, sum is an integer type variable. So sum is equal to sum plus x, we are adding mathematical operation. Plus is a notation that we use to add an element to a list. And how we add that element? In form of a list. So basically plus basically means that we are appending two lists. This is the default actually, the last one which you see here, right? So we are appending two lists, this plus this, and we will just simply write all those elements in that sequential format itself in the final list. But here when we talk about adding an element, we will create a list of that element here. So if we just want to add 3 into this list, we will write that 3 itself in square brackets. So square brackets is the notation of a list. And we can do that at the back, we can do that at the start also. So what do we want to come first? In this case, we want to add 4 to the beginning, right? So we will first write this 4, then plus, then whatever we want to come after that. So the whole list. Next we come to the concept of nested iteration in a list. So for each X
so in the
encoding,
above portion, the plus was you're appending the list in the end.
So it all depends on
Like
on
the
what
dummy
we are
list
actually
plus
adding it
3.
to. Yeah, so when we say dummy list 3, right, we are just adding two lists here. There is no notion of appending to the back, appending to the front. Why? Because we are creating a new variable itself, right? So it's just a combination of dummy list and dummy list 2. But in which the order in which we are appending is dummy list will come first, the elements of dummy list will come first, and then the elements of dummy list 2 will come in that order, correct? But here what we are doing is, we are in dummy list itself, we are changing that, okay, dummy list by itself, whatever is there, it should be there, but then we want to add another list to it. So even though we are changing this, what we are changing is we are already using what that particular list is in order to change it, just like we do in variables, like sum is equal to sum plus x. So we are changing the value of sum by using the value of sum, correct? So in this case, we say that since this is same as whatever we are trying to put it in, extending at last means doing like this, or extending at the start means writing it like this. But essentially what we are doing is, we are just simply appending two lists to each other. So first list, then plus, then whatever second list is. Understood? Any doubt
Yes,
here?
Except of starting and ending.
Your voice again, I was not able to hear it completely. It came briefly. So can you repeat?
Hello, am I audible?
Yeah, you're audible. Can you repeat the question?
Hello. Yeah, so can we add elements anywhere in list except of starting and ending?
No. So here we will be adding in start or end only. So this notation is start or end only. If you talk about adding anywhere, then we have to do some other tricks and stuff to kind of simulate that.
So
But by the convention given
it's
to us in the
possible.
computational thinking. Yeah, please go on.
It's possible that we can append in between with any procedure or code.
So we will have to write a custom code for that, right? We'll have to maybe break it. So we in further weeks we saw sorting, right? Week 6 we saw sorting and stuff. So in that case we will have to go through. So if we want to, we will basically have to break up that list first into different variables and then see where we want to add that new variable and then construct a new list from that. So that is the procedure of adding that particular thing to one particular. We will come to that. Okay. So again, now we have nested for each. So for each inside another for each was there. So one example is that we found out whoever scored minimum in coding, and we found out whoever scored minimum in quiz and gaming. So we got these particular lists that again, why was it a list? Because let's say whatever minimum marks were there in coding, right? Let's say multiple students had that marks. So instead of having one variable as whatever that particular person was to compare, we need a list now, because multiple students can have that minimum marks, right? So we created that list for all of them. Coding minimum in coding min 103 and 105 serial number had minimum marks. In quiz min 101 and in gaming min 102 and 105 again. Now we want to figure out whether there is somebody who has scored minimum in at least 2 of them or in all 3 of them. So this is the logic for that. So we check coding min, we check Y in gaming min, and we see that okay, is something matching? If it is matching, then we create a new list, coding gaming min. Somebody who has minimum in both coding and gaming. And then we will compare it with quiz. So if there is one particular student who has minimum in all of them, who has scored minimum in all 3 criterias, then to find that student, this is the procedure which we'll be using. So first we'll do coding gaming min, and then we will do with this new list coding gaming min, we will compare quiz min and then find out what that new person is. Okay.
that means who gets least in all the 3.
Yes. So independently we find out who scored the least in that particular subject, and then we want to find out that is there some common student who has done poorly in all of them. For example, this is basically a different version of that topper problem, right? That 3 prize problem. That is there a particular student who has topped in all 3, or who is among the toppers in all 3, or top 3 in all 3 subjects, right?
Yes, ma'am.
So this is sort of a analogous problem, but in a minimum format. Now coming to some formats of list. So L is defined in this way. We say that length of L will give us the number of elements in the list. First of L will give me the first element of the list. So 3 itself. Last of L will give me the last element. So these are returning elements. But rest of L and init of L. So rest of L is basically everything except the first. So this will return a list itself, not a value, but a list itself. Init of L will return me everything except the last value. So again, a list is returned. Member L comma E. So this is a particular helper function in which if E is in L, then it returns true, otherwise it returns false. E is an element, L is a list. So the first parameter for this member helper function is a list, and the second parameter is an element. If that element is present in this particular list, we will return true, otherwise we will return false. So there are certain combinations that we can use with these particular helper functions in order to do multiple things. So let's say last init of L, we want to find out second last, we want to figure out first, second. So these things we don't have, so first is there, but second is not there, right? But let's say I do first of rest of L. In that case, we are able to find the second one. Rest of L
Yes.
is 79015. But first of this particular rest of L is the second overall. So we can find such things. And overall, these are two things which it's good for you to remember. One is that
Ma'am, there's plus plus so that increment.
no, plus plus is not increment. Plus is increment. Plus plus is appending. This is what we discussed here for 10 minutes.
Okay, ma'am. Since I was late, that's why.
Okay. No, you can even see the recording again if you missed anything. So this is again, L can be reconstructed by appending the first of L in a list format to the rest of L. So this rest of L itself is returning a list. So we are writing it without any square brackets. But here first of L is returning an element. So we need to add the square brackets ourselves and then append it to the rest of L list. Similarly, init of L, which is all the initial part of L, everything except the last, plus appending the last element in the form of a list. This is how we can recreate a list using
Ma'am?
first and rest. Yes.
That means the first question's answer first of L is 3 and plus plus rest of L, that means 9015 or 79015.
79015, right? Rest of L. L is this only. We are not changing L anywhere.
Okay.
This is just we are trying to figure out things from L, but we haven't changed L anywhere.
That means first of L we will keep 3 in the form of list in square bracket, right? Plus
Yes.
plus 79015. Okay.
Yes. So overall, we will get the list back.
Okay, ma'am. Clear. Thank you.
Excuse me, ma'am.
Yes.
Yeah. Can we treat all of them as a function?
Yeah. So these are helper functions only, right? So yes, these are procedures that are written in the backend. So we don't have to write it ourselves. But whatever operations, so some hidden operations are there in which we are getting this particular one. So let's say we are talking about last of L, right? So some computation is happening in the background of last of L. This is the function itself, which is in which we are passing L. So these are called helper functions, which we are passing L, and then automatically whatever output we are getting, we don't have to care about how we are getting that output. We are just getting that output. So we can use it directly in a function or in a pseudocode that we are writing.
Okay, suppose if there is a list which is empty, so if we apply first and last, then the result will be error, right?
So depending on the context, it could be an empty also, or it could be an error also. It depends on the
Ma'am,
definition of
if we merge the rest of L and init of L, then it will become L.
No. Why will it become L? Rest of L is itself a list. Everything except first is there. Init of L is everything except last is there. So if you combine this, a new list will be made which has no relation to the actual L. So it will have 79015, 37901.
Okay, ma'am.
And ma'am, if a list has only two elements and we apply init of L or rest of L, then will it give in a list form or only value?
It's list form itself. So it doesn't matter how many
Okay.
things are there, it will give in a list format.
Even for the empty list.
For empty list, I will have to check the notations actually once. So maybe you can go through the slides on your own once, but I'm not sure if it will give an error or an empty list.
In that member, only true and false.
Sorry?
In that member, there is only true and false.
Yeah, member will return only true or false. Whether it is there or not, that is the question.
Okay.
So any doubts here?
If a list has only one element, then the rest of L will it give error or empty.
Empty. I think it will give empty.
Can you please repeat the question?
If a list has only one element and we apply rest of L, then what will it give?
Empty list.
Hello. If you can
Uh,
explain this, the green written to code further.
Yeah, so here what is happening is we see that first of L is returning a element.
Yes.
Are you able to hear me? Yeah,
Yes.
first of L is returning an element. So whenever we are trying to append, we can only append two lists to each other. We cannot append one particular element and then a list. So two lists get appended to each other. So in order to do that, we first have to create a list from that element. So first L will return an element, and then we can add that what is first and rest doing in terms of the logic. First is
The whole
returning the
list.
first, and rest is returning everything except the first. So in order to get back L, we have to join them, right? Join them using plus plus. So plus plus is appending, and here we are using the square brackets because it's an element. So we
So
first have to
basically, we
convert it
can
into
say
a list.
that they both are the subset of that L.
Yes, and not just a subset. Subset, rest and init are also subset, but if we combine that, we are not getting L back. So they are mutually exclusive, and again,
Yeah.
when we combine them, we get the full thing also. So they are mutually
Yes, ma'am.
exclusive also, and they are exhaustive also.
Yes, ma'am. Understood.
So everybody, any doubts till here? Everything is clear till here. So after this, I will just continue with lists a little bit, and then I'll introduce the notion of dictionaries.
Yeah, ma'am. Understood.
Yes,
Okay.
ma'am.
So now here, just one more thing I want to introduce that was there in the initial weeks. The concept of binning was there. Okay, so given that, let's say, I'll introduce one new problem here instead
Yeah,
of just repeating.
that reduce the iteration.
Yeah, so something which we till now, you see, whenever I talked about nested iterations, right? We did everything. So we compared everything with everything. We were not doing anything smart there. We were comparing everything with everything. Even if we think about, reducing the computation in some way, let's say I have, okay, just give me a second. Yeah, so let's say we have, we are comparing different students. So let's say first I compare student 1 with all the other students. So we are comparing with 2, 3, 4, 5. So 1 gets compared with everybody in that first iteration. Then let's say I'm comparing student 2, but instead of comparing it from 1 itself, I start comparing it from the next student. So 3, 4, 5, right? So for
Because
each x and for each y, we compare x and y. So even in that case, the total number of comparisons is what? N into n minus 1 by 2.
Yeah.
Right? Simple maths is there. So n choices were there for the first
Basically,
student.
10 will be.
Yeah. So n choices were there for the first student, n minus 1 choice for the second, and then that same thing is getting compared again and again. So n minus 1 by 2. Basic combination, permutational combination, right? But now, even for 100 students, that would mean that how many pairwise comparisons are there? Approximately 5,000, a little less, 50 less than 5,000, right? Approximately 5,000 comparisons. That is a lot, right? Especially if suppose, let's say the problem is that that birthday problem was there, right? We had to figure out how many students were born in, do they have the same birthday or not? So in that problem, we are comparing each student with each other student. Everybody is getting compared with everybody. So do we even need to check everybody? Given the nature of the problem, a person can only have the exact birthday if their months are matching, right?
Yes.
Yeah.
So
Yes.
instead of checking everybody with everybody, and whenever we are doing something nested, right, we multiply the number of computations. It's a lot. It increases dramatically. So instead of doing that, if we try to first bin the people instead of comparing nested format, we try to group these people into certain sections, and then we know that whatever logic we want to apply next, we don't need to compare everybody with everybody. So we
Yeah,
try
it
to
will be smart choice.
yeah, so we try to segregate the students in such a manner that we know, okay, all these are born in January, keep them in one bin. All these are born in February, keep them in one. Similarly for all the months. Now we only have to compare in that particular bin. So the number of comparisons will change. It will decrease. So binning is basically the core idea behind binning is that we are using some property of that data to partition it so that the impossible comparisons, the comparisons which we definitely know will not yield anything, they get eliminated. We don't even need to do that comparison. So answer won't change. It's just the number of comparisons will decrease. That is the concept of binning. Okay. Binning is clear.
Yes, ma'am.
Okay. Next we talk about okay, so list again is clear. We needed some collection. A single variable was not enough. We saw some list operations. We saw some list functions. So I hope that is clear to everybody. Length, first, last, rest, init, and member. Okay. Now coming to we saw for each also. That is also clear, right? We were doing some filtering with lists. So if suppose something is satisfied in that particular list, then we do some
Ma'am,
appending.
excuse me, ma'am.
Yeah.
Ma'am, in that binning, is there any concept of that factor of reduction or formulas?
Yeah, so there was one particular formula. Let me just share the slide for that one. It will be easier to go by the convention that we have here.
Basically, I have that formula, but I can't understood that, ma'am.
Yeah, I'll just discuss that once. Can you see my screen? This slides, are you able to see?
Yes, ma'am.
Yeah, so this is what we discussed earlier, right? So n into n minus 1 by 2. This was clear?
Yes, ma'am.
So this is basically NC2 combination of n objects, 2 at a time. Okay, so we are comparing 2 at a time and we are comparing n things. So overall, n into n minus 1 by 2 comparisons need to be made. This itself is a smart choice. We can do even more than that also. Technically, it could have just been n square also. That we compare A with B, then we compare A with A also, and then we put some if conditions like we were doing earlier also in some pseudocodes you might have seen. That is a very naive approach. But total number of pairs was n into n, right? But it first itself we are filtering that, and we don't want to check two same things. We don't want to compare two same things again and again. So after doing that reduction itself, we have come to n into n minus 1 by 2. But even in this, given the kind of data which we have, this part is clear, right? Number of comparisons. But even in this part, it is growing very quickly. When n is, let's say, 100, we are making these many comparisons. So some quadratic curve is there in terms of comparisons. Why? Because this is of the order n square. N into n minus 1 when we'll do, it's n square minus n, right? Removing the constant factor. So what do we want to do? We want to reduce the number of comparisons. So this is where we are using binning. So first we will, let's say here in this case, we say that the number of comparisons had to be 36 for these 9 objects. But if I divide these 9 objects into 3 particular bins of 3 objects each, in that case, what do I have to do? I have to compare these 3 with each other, right? So how many comparisons in one particular partition? 3.
Yeah, 3.
And then again, how many partition comparison in this? 3. So 3 partitions, 3 comparisons I'm doing 3 times, right? 3 comparisons 3 times. It gives me 9. And then again, those 3 I will compare. It will give me maximum 12. So initially I have, okay, 3 comparisons 3 times. It's giving 9. So it is reduced by a factor of 4 times. That is one thing. But even if that particular thing I have to compare again, it will be maximum 12.
Yes.
So now we see the reduction. So for n items, earlier the number of comparisons were half into n minus 1 without any binning. Now if we use k bins of equal size, k bins of equal size means that we are dividing the whole data set which we have into k parts, all of equal sizes. Then the number of items in each bin is n by k. This is clear? Earlier we saw it was 9, so 3 by 3. 3 bins, 3 sizes, 3 particular bins, and total 9. So each bin will have 3 elements now. Number of comparisons per bin is half into n by k minus 1. This is also clear. Any doubt here?
So only that basically we used to divide only by k.
Yeah, so we just need to divide n by k. So n gets updated to n by k now. Why? Because that is the new number of items in the bins, right? And in the end, we just multiply with the number of bins which are there. So factor of reduction, we just divide. This is the basic maths here. That factor of reduction is initially how many computations were there, divide by the new number of computations which were there. And this is what we get. So we can just input n and k here, and then we will see how much it is getting reduced.
So to get to obtain total number, we lastly we used to multiply by k.
Yeah, we will multiply by k. Why? Because that itself is getting these number of comparisons which we have reduced. It is getting repeated k amount of times, k number of times, right? For each bin.
Okay, okay, okay.
So then that will give us, after the computation, you can try to write this by hand once, and after this, the factor will be this. So you can even derive this at the end. It's not an issue. Okay. So this was week 4. If I go by the slides itself once, week 5 has been covered more or less. Coming to week 6. So we had sorting now. Okay. Next we have is sorting. So what was there in week 5N? So list functions we completed, right? Week 5 we have completed. Coming to week 6 briefly, we will. So week 6 is just an extension of what we can do with lists, and then they have discussed some examples basically. But sorting, basically we want to make some computation simpler. So finding duplicates. So this is basically the intention. I expect you to go through the slides on your own. So I will just try to give some intuition of sorting. Yeah. So one operation is that, let's say we want to add a new element, but to a certain position to preserve order. Right. So first of all, the first thing is that if I, let's say I have marks of different students, they are in a random order. I want to first find out the top 3 students. Then if I have a list already, I can just sort that particular list, and then I will have the top 3 students, or at least not the students, the top 3 marks. The top 3 marks that have been attained in that particular class, I will have that. Correct?
Yes, ma'am.
And now let's say I want to insert something new. So I have to insert that in a correct position, and I want to preserve that particular order which has been there till now. So let's say I have this particular list here. Okay, 10, 20, 25, 37, 45, and let's say 70. Okay, some random list is there. Now this is in ascending order for now, correct? Now I want to introduce, let's say 30. 30 is a new element I want to add. Add an element 30. So somebody said, right, how do I add something in between? Just give me a second. Let me. Get my charger.
So it will be put in between 25 and 37.
Yeah, so it will be put in 20 in between 25 and 37. But how is the case? So we said, right, that we'll discuss it later. So that later has
We have to
come.
write some pseudocode for it.
Yeah, we have to write some pseudocode for how we will insert that in the middle, right?
Yes.
Yeah. Yes. So now by logic, we can see that it will come between 25 and 37. But what we will be focusing on is the algorithm of insertion sort. So what insertion sort will be doing is we will be focusing on, there are multiple sorting algorithms, but the one which we'll be looking at here is insertion sort. So what insertion sort does is that the basic idea is this. We start with an empty sorted list. So basically in that empty list, I'll keep on adding some stuff. I'll keep comparing whether this element needs to be added at this point or not. And then I want to insert it at the correct position and then repeat. So for any arbitrary list also this can be done. Okay. So let's say my input is, so I'll be doing it for some arbitrary list. Let's say this is my input. So my input is 40, 10, 70, 20. Okay. Right now you can see this is not at all. This is not at all. Guys, some participation, please.
It's not sorted.
Yes, yes.
Sorted.
Yeah, it is not sorted, right? Just give me a second. I'm getting some issue in my laptop due to the charge. Just 1 minute. Yeah.
It will be not sorted.
Yeah, so earlier we will now for each, so I want to start writing a pseudocode for this basically. For each x in, let's say this is L. For each x in L. What are we doing? So first of all, for each x, for the first element itself, there is no comparison, right? So I will append it to the new list.
Yeah.
Let's say I have some sorted L. I'm not initializing it for now. So sorted L equal to sorted L plus plus. Here we have sorted L, an empty list. Sorted L is equal to sorted L plus plus x. This is for the first one. I did not make any comparison for now. This is not logically correct. I added 40. Then I have 10. So what is the logic here now? I mean, I won't be writing the exact pseudocode for it, but some logic here is that first I will have to check something. Some logic?
Yeah, it will be checked that either greater or less.
So basically, somewhat a nested list I'll have to do here. So for each y in L, or sorted L. So you see what we are trying to do here. For each y in sorted L, what we are doing is we are comparing the current y with the x. So if whatever x we are getting is smaller than the current y in L, the first y in L, then I am appending it in the beginning, right? Everybody is following this?
Yes, ma'am.
Yeah. Yes.
In that case, we are
Can
appending in the,
reiterate it?
sorry,
Can reiterate it?
your voice is not clear.
If you can reiterate.
Yeah. So we will reiterate for each element, right?
I mean to say if you can repeat it.
Oh, okay. So basically, so rather than, okay, I'll just, for the sake of time, right, I will try to show it through this particular. Is it visible?
Yes.
Yes.
So here, so this is exactly what I was trying to build the intuition for in the slides, but since I think we only have 20 minutes left and I want to cover dictionaries also, we will look at this particular slide itself for the insertion sort pseudocode. So basically, this is a procedure for insertion sort. It is taking a list and we will first initialize a sorted list. Then for each element in the actual list, the unsorted list, we will change the sorted list. Basically, the sorted list, every time we are doing it, we are sorting this particular list through this another procedure or function call. And this particular function call has been defined here. Procedure sorted list insert L. So this particular procedure will always return the sorted list L after appending X at the correct position. Understood? So in this particular escalator we saw, right, that there was already a sorted list which was there, which was L, and in that particular sorted list we are appending X. So the logic for this is what I was trying to do, that for each Z in L is already sorted, right? Why is it sorted? So that part was done here. For each Z in L, sorted list is equal to this particular thing. So the first iteration that I was trying to do was this. The second list, the second particular nested iteration was this now. For each Z in L, if not inserted. So inserted is false. Initially, this is a flag condition which we have. If not inserted, which is if true, we have to check if X is less than Z. If X is less than Z means that the first element in the sorted list itself is X is smaller than that element. Then I am simply adding it to the end. So this is basically, I think, in ascending order, we say that it is there. And we want to insert a new element so that the list remains sorted. So if that particular Z in L is, that particular Z is greater than X, in that case, we will append that particular X to the current list which is there.
Yes, ma'am.
And we say that inserted is true. That okay, we have inserted something inside it. And now new list is equal to new list plus Z. New list was empty.
Yeah.
So the first element in new list was X itself, right? That is what we checked, right? That for each Z in L, if from the first element itself Z X is small, then
So
currently X is the
X is
smallest
less
one, right?
than. So X is less than the current element that you are visiting. So in that
Yeah.
case, the
Yes.
new element, you are appending it to the left-hand side.
Yes, exactly, right? Because X is the smallest, right? So currently new list, for the first iteration itself, new list is empty. So new list plus X will give me X only. Now after
Acha.
that, yeah, so this is just giving me X. It will look like X is getting appended to the end, but actually X is getting appended to the very beginning because the new list is
Yeah.
empty only for now,
Yeah,
right?
new list is empty, then it will become first member. That's
Yeah, so inserted becomes true that okay, now we inserted this particular thing to the new list. Now this is getting true only if X is smaller than Z. If that condition is not fulfilled, then we will first append Z itself.
Z itself in the new list that will become.
Yeah, and now the second condition that we are checking here outside of the for each is that if it is still not inserted, then we are appending it to the end. Are you understanding this particular point?
That means it's the largest of all the ones.
Yes, exactly. That this means that it is the largest of all.
Actually, the same code is being written in the here and the two line above. So that way the confusion starts.
So this is
Ultimately, it will
happening
say,
inside the comparison of the list. But if in all of these cases, if this if condition fails, then we are not inserting anything here, right?
Okay.
yeah, then if
Then insert will
not
never
insert.
be true. In that case, we are just appending Z. The current Z is already sorted. We are appending that again and again and again. And at what
Okay.
point are we appending this? So I told you, right, that instead of, you said, right, how to
In that
insert something in the
case,
middle.
so X is empty. So in that case, can't be X be written on the left hand side? Then plus new list.
Yeah, that can also be done. So since it's empty, it doesn't really matter, right? Whether we have something plus empty or empty plus something. The answer is something only, correct?
Okay.
So this logic is clear to everybody. First, we are checking inside the particular list which we have comparing. And if all the comparisons are false, in that case, we will simply append Z itself. And in the end, if inserted has not been true, that inserted basically is a flag that has the current element been inserted to the list or not. If all the iterations for each Z and L, it does not get inserted, then we have to
Ma'am,
insert it at the end, right?
if that man X and Z both will become similar, then
If even then it will be in the end only, right? Because this is less than sign only.
okay.
So even then we will add it to the end only. Or basically after that particular element somehow.
So ma'am, basically if the list is empty, we will directly add X in the last, right?
Yeah, so that last basically means the first only in an empty list, right?
Yes, that's what I'm trying to say.
Yes. So this insertion sort is clear to everybody?
Yeah, ma'am.
Yes.
Okay, so you can refer to this particular pseudocode itself for that instead of the Excalidraw setup. I was trying to build the intuition, but we're short on time. So I'll directly move to the dictionary part now. So again, for this, you can, there were some more slides, I think, in insertion sort. So summary is there. So basically the uses of insertion sort have been mentioned. That first of all, sorting is a pre-processing step and an important one. It's a natural sorting algorithm, and we are repetitively inserting a new element in a original list into a new sorted list. So, and again, we can reverse the comparisons to sort it in descending order. So all these you can go through the slides once. Coming to week 7. So 2 weeks are left. Both of these weeks handle dictionaries. One is the general intuition of why dictionaries are needed. So that has been detailed in, that has been explained in a lot of detail in the week 7 live session. The second one, I think. And just to reiterate, this is what I had discussed in that session also. But just to reiterate once, the structure of a dictionary, why we need a dictionary is that lists were there, but lists, we have index or position in lists and everything is ordered. But let's say we have to compare the customer IDs of a customer are 1, 2, 3, 4, 5, and the corresponding names of those customers are Namit, Shreya, Rohit, Ananya, and Jack, right? But let's say we want to do some computation or some comparison related to the names as well as their addresses, the city or the address which we have mentioned here. In order to compare those, we need some notion of where that value is in that list. So Rohit is the third element, right? Or the second index element. So in order to find out where Rohit lives, in the address list, I will have to iterate first and go till the third element, correct? Everybody is understanding this?
Yeah.
So basically here, the notion is that customer ID is 0 is the ID for name of 0 who lives in address 0. So customer ID 0, which is in this case 1 customer ID is the ID for Namit who is living in Delhi. 2 is the ID for Shreya who is living in Chennai. So these are all the notions which are there. But this is very complicated. We'll have to make many more lists for each field. And then if some person gets deleted, we will have to iterate again and again. And this is okay for 5, but let's say we have hundreds, right? We can't have lists with hundreds of elements, and we have to keep keeping the notion of that order in order to do any computation. This becomes very complicated after a point, right? So now what is better data structure for this is a dictionary. In a dictionary, we have something called a key value pair. So a key will denote whatever is unique for that particular value. So one example is for this particular data which we had, or rather the student marks data set itself, right? Let's go directly to this one. Key is the card number. Why? Because it's unique. So key is the card number and value itself is a dictionary. So a nested dictionary, we can say. Inside a dictionary, we have a dictionary in which key was the card number of that particular student, and that card number denotes a set of values for that particular student, such as name, city, gender, date of birth, and marks. So that itself is a dictionary where the field name becomes the key now. So name is a key, city is a key, and this gets repeated for all the cards. So 1 is the key for the first card that has all the information for that first card, and 2 is the key for the second card, and this whole is inside another dictionary, the master dictionary that we have. And again, this is nested till 3 levels. So marks again is a nested dictionary of maths, physics, chemistry, and total. Correct? This was all for these fields. So from these fields itself, I have created a dictionary for the entire data set. That much is clear?
Yeah.
So again, dictionary, the initialization of dictionary is through curly braces. Key value pairs are there and key is unique. This is the basis of how we are going with the dictionary. And the notation of adding something is D of key is equal to value. So for that particular key of that dictionary, if we want to insert this particular value, this is how we add it. And that value can be anything. It can be a string, it can be a number, it can even be a list. It can even be another dictionary. So for example, here what we are doing is D of 3 is Rohit, Bangalore for the earlier data set which we were having, right? So D of 3 was the customer ID. Customer ID was key. And in that customer ID, I want to add all that information about that particular person that is there. So in this case, it was Rohit Bangalore as list. But a better way could be that even in this, I would have had a name, comma place, comma price dictionary. It becomes more intuitive also. So that improvement. So I first introduced this example, and then that improvement I did in the student data set. This is even a better way to represent this data. Another example or a pseudocode for dictionary was this. So counting the number of MIS, so basically all the numbers, counting the frequency of the numbers in the word Mississippi. So we initialize the dictionary like this. Then for each C in word, so word was that string which we have, for each character in that word, we checked whether isKey DC is again a helper function for dictionary. So what does isKey DC do? That is the key C present in the dictionary D. If that is true, we will enter. If not, we will enter the else. So if this is true, that if already C is present as a key in D, that means that that particular alphabet has already been encountered by the dictionary key, right? So in that case, we are just incrementing it by 1, that the frequency of that particular letter, we want to add it by 1. If that particular C character is not present in the word or the dictionary till now, then we will introduce this. So D of C is 1 will basically add a new key C which to the dictionary D, and the value for that will be 1. So you can try running that once for yourself and see how this will happen. Okay. Now accessing. So there are certain operations that you can do with the dictionary. One is that you can update the data with a new key value pair. So if I do data 3 is equal to this, right? So data of 3 now becomes, even if there was some data initially, now it becomes an empty dictionary. So we are updating something. Next, accessing something. So data of 1. So the key 1, data of 1. So again, when we access something, we are doing it like this, using square brackets.
Data of 3 will actually give you the list of the inner dictionary.
It depends. So here, right, in the green part that I have written, in this, I am basically saying that data 1 contains this. I'm not initializing anything. I'm saying if I call data 1, then this is what I will get in that variable.
Yes.
But here I'm saying I'm updating it. So this whole expression is what I'm writing. That data 3 is now an empty dictionary, so it will update that key value pair. The value will get updated for the key 3 using this whole expression. But here I'm not updating anything. This is D of key itself, and that is a way of accessing the values with key and not a list index basically.
Yeah, basically
So
that
usually
key
when
of
you
one.
usually when you do data of 1, right, your assumption is that data might be a list and I'm accessing the first basically the index 1. So say second element I'm trying to access. But it depends on what data is. So if data is a dictionary, this is a key. If data is a list, then this is the index. That is very important distinction, that you have to know first what data is. So you have to go and
If
check the
data is a
initialization of
list,
data.
it's an index.
Yeah, it's an index. It's a way of accessing the index.
And if
But if
data
data
is in the curly
dictionary,
braces, then it's
yeah, if data is a dictionary, then this
Basically,
is the way of accessing the key, the value for that key.
basically in that expand form.
Yeah.
no. If it's in square bracket, then you are trying to access the values for that dictionary. And if it's not in
Yes.
the
So if this is what is giving, right? Simply if I have data of 1 and we know data is a dictionary, then whatever this will return is the value for
the
this
values for
given key. This
yeah,
given key in the bracket.
key.
So in this
Got
case,
it.
it was this. Name was Nidhi,
And
city was
if
Chennai.
it's data and then curly braces, then you are updating the data.
No, not curly braces, not just this. It could be anything. I could have written something inside this. But the difference here is whether I'm giving this full expression as a statement or whether I'm just asking what will this return,
They
depending
both
on the
are
question.
different.
Yeah. Okay. So data of 1 is this, but now this itself is a dictionary, right? So data of 1 of marks, and that will give me this particular thing. So this is how we access multiple things. So data 1 of marks, even in nested dictionaries, even in nested lists, we were doing this, right? Data of 0 of 0.
Okay, we goes to our deepness.
Yeah. So this is how we will go. Once you will go through the pseudocodes, right, you will understand the distinction pretty well when we are accessing something, when we are updating something. Now, in this case, we are updating an already existing key value pair. Data 3 already exists. It was empty. Now I'm updating it with this. So in this, I'm not accessing something. I'm updating something. So again, the distinction is not clear just by looking at it. It depends on the context. You have to understand the context.
Okay, then data of 3 of name will become action.
Yeah. Now, okay, this is the end basically. This was another example that we were going with roll number, name, and attendance. So we basically had to find that for a particular roll number, the name is this, the attendance is this, and then there was some pseudocode in which I was trying to show how to work that dictionary in a pseudocode. So while was there, dictionary was initialized, and d x dot roll, I added this particular thing here, that name is x dot name, attendance is x dot attendance. So this is initializing that dictionary. So I filled that dictionary with the data that was there. Okay, and this is the finding the, so the task was finding the average attendance. So this is using that dictionary. So for each key in keys of D will return a list of keys of D. Keys of D gives us a list of all keys in D. So here keys of D is 1, 2, 3. Is key D K, does dictionary D have key K? It returns true if yes, else false. And this is how we access things. D of K of attendance gives me the number, and then I'm adding that to the total. Understood? This part is clear. The pseudocode is clear to everybody. I'm just simply using a dictionary. I'm first initializing a dictionary. I am filling that dictionary with data, and then I'm using that particular dictionary.
Ma'am, this hashtag line did it shows that what is happening in the code.
Yeah, this is just a comment. You can consider this to be a comment. Otherwise, just remove it also.
Okay. To summarize that, what is happening?
Yeah. So what is covered in week 8 is now, so only week 8 is left, I think. What is covered in week 8 is that in this mostly the value, in the key value pair, the value was either a string or a number. But in week 8, we introduced the notion of that particular value being a list itself. And then there is certain computation with that, right? So that is the initial of week 8 that I had. Then it comes to side effects. So again, side effects I had already introduced in week 4 revision. Dealing with side effects, again, when we have some nested loops, like you will notice here that the list itself will get changed. So overlap is getting changed with something. Now, what if we we were using the overlap in some other, let's say, notion. Let's say comparing two lists for duplicate items is happening. So a nested loop is there. So if the lists are already sorted, let's say, then we need not start an inner iteration from the beginning, right? We can use first and rest. We saw this, how to reduce the computation. But in that case, second list itself got modified within this procedure. How did it get modified? Find overlap, L1, L2 were passed as procedures. And the overlap was in the list itself, that okay, which particular elements are there in both the lists. So since it is already in an ascending order, so we first just check the first element of L2, and then L2 was the rest of L2. Now L2 is getting modified here, right? In the second iteration itself, L2 changed to something else, correct? Right?
Yes, ma'am.
So the L2 that was passed here, now L2 got changed in between this computation. And now whenever I'm doing this here, right, first of L2, then that first of L2 is again second.
It's a second element.
Yeah, so this is a side effect. Now it can be intended, it cannot be intended based on the pseudocode which is there. But an ideal thing is that instead of changing the list itself, we should have made a copy of that particular list. And especially if it is an input parameter of a procedure. So we don't want to change that itself. Why? Because if L2 is getting changed here due to the procedure, and we are using this L2 somewhere else beyond this procedure, in that case, we are already getting a modified value. We don't want that, right?
Can you tell me how to copy a list and make a duplicate of?
Here, basically, this is how we are copying the list. My L2 is equal to L2, and now we will do everything with my L2. We will leave L2 as it is.
Okay, thank you.
And why was it needed? Even though here we wanted to modify L2, but at the same time, L2 is being passed as a parameter here, right? to this particular procedure. What if I'm using L2 beyond this procedure somewhere else? I don't want it modified there. I want the original L2, right?
Yes,
So
ma'am.
in that case, we will just make a copy. Similarly, deleting a key from a dictionary can also cause some side effects. So this is just go through these particular things once. Sorting a list and deleting a key in a dictionary are convenient side effects also for updating collections in place. Sometimes we want to change it, sometimes we don't want to change it. So based on that, we have to decide what we want to do. Okay. So this was basically week 1 to 8 summary. And questions will be discussed in the next session. And if you have any conceptual doubts, please feel to post it on discourse. And I think yeah, this is all. I'm closing the session now. I hope it was clear to everybody. And thank you for your time. Thank you, everybody.
Okay, okay.
Yeah.
Thank you.
Thank you, ma'am.
Hello. Hello, anyone is there? Hello.